if they don't have the capacity, the automotive people, designers are not going to design with a lot of aluminum for fear of a shortage, and then their prices are going to skyrocket. And the people who make aluminum don't want to spend the money to put in the capacity unless they can know there's a market. Okay, so they try to work that out. The Department of Energy tries to get in and help things out, but they're not much good at that either. Okay, so far as that goes. But if you look at some of these other things, they once wanted to use an alloy which is very similar. Actually, it's the predecessor alloy for what is now HSLA 80. Okay, there's HY80 that was developed in the 1940s and 50s by U.S. Steel, that was used in the Nautilus submarine and was used until recently on other subs, recently be 20 years. They built a couple of HY100, which is actually the same composition, just a different heat treatment. Okay, to give you HY100, the Navy in the 1960s developed HY130, and we've never really used it for a full-size ship. We can talk about why they haven't. I had to go meet with the chief engineer of the Navy once and tell him why he shouldn't. They were going to promise Congress around 1990 that the third or fourth ship in the Seawolf class, this is before peace hadn't broken out with the former Soviets, they were going to, after the first 2 or 3 ships, they were going to start making HY130 ships, and the people, David Taylor, had been trying to tell the people at NAVSEA that they couldn't do it, even though and then people at NAVSEA, well, we spent $50 million in 1960 developing HY130, why can't we weld it? Well, if you weld only a certain thickness under certain conditions, you can weld it, but a real submarine actually has to have different thicknesses, and and not necessarily under those conditions. And so from a practical point of view, HY130, you can use it in specialized applications, but you couldn't build a whole ship out of it. So the Navy started looking in the 1980s and 90s at developing new steels, which are the HSLA steels, and you have HSLA 60, HSLA 80, HSLA 100, I think, but I'm not sure if they've ever used it. Of course, the sub guys will not use anything but the HY steels for the hulls because they're conservative, and the surface ship guys will use whatever will give them more surface ships, which is the HSLA steels, because they're more weldable. In any case, back when I was working for Bethlehem Steel in the mid-70s, they wanted to use the precursor to the HSLA steels, which had 1% nickel in it, to build the Alaskan pipeline. And because nickel adds toughness, okay, you won't get brittle fractures. It would have used a substantial fraction of the nickel in the world, okay, to build that one pipeline and other pipelines out of that steel. Now you can build a few ships, but when you start building whole pipelines, it actually takes more steel than to build a few ships. But in any case, nickel is expensive, and you can come down here. There's, neodymium. I put that in there. Anyone know why I put neodymium in there? First of all, I found the data, okay? But neodymium is how you make very strong magnets, okay? The neodymium iron boron magnets, that's another story. Okay, so we have a strength, toughness, availability, and you also have relative cost, and we're going to go through cost a little bit here. Steel has a unique combination of strength, toughness, low cost, ready availability, fabricability, and repairability. Okay? It's got all kinds of, it's just sort of a sweet spot material. Okay? Which is why people make 1.5 billion tons in the world. Okay? So they like to make, we like to make steel, so far as that goes. And we like to use it because it's cheap. So, so now let's start getting into welding metallurgy. We will talk about aluminum and titanium and stainless steels and things like that, but you're probably gonna say over the next few hours of lecture, why is he spending so much time on steels? This is why I'm spending so much time on steels. Okay, so here's another handout. This is, how many people have ever seen a phase diagram? Okay, about half of you. Okay, you don't have to learn about phase diagrams because you're not going to be quizzed on them, but they can be useful things. I'll pass out the phase diagram, but before I do that, here is one of the other ones I just passed out. Materials research to meet 21st century defense needs. It was some committee I served on back in the early 2000s. And the Defense Department decided, why don't we figure out what materials we're going to use in the future? It turns out people are always debating this, okay? And you read in the Wall Street Journal and places about some new material, and you read about nanotechnology and all this other stuff. And in general, nanotechnology is good if you're going to make some sort of fancy optical material or electronic material or something, a functional material. But nanotechnology is sort of useless for structural materials, which is what this course is supposed to be focusing on. How do you build something big? You don't make something big out of something that's super small, right? But you'll read all kinds of people, oh, well, we can come up with something that's 10 times stronger than any material we have right now. Yeah, and we did that 60 years ago. We made iron whiskers that had strengths of 2 million psi. HY80 is only 80,000 psi. The problem is, the only way you can do that is if you have a single screw dislocation, crystal imperfection right up the center, and no other dislocations, because dislocations are what make steel malleable, that you can form it and shape it. So if you get rid of the dislocations, the inherent strength of the steel is about 2 million psi, and when you take the video stuff on adhesive bonding and stuff, I'll prove that to you, okay, on those lectures. We knew that, okay, but you read about buckyballs and bucky tubes and, you know, carbon fibers, and these things are going to, you know, the physicists have calculated that the strength of these things will be fantastic, millions of psi. Well, you know, physicists and material scientists did those calculations in the 1930s. But some guy who wasn't even born in the 1930s comes along and he says, oh, I just calculated the inherent strength of a carbon-carbon bond. And it could be millions of psi. Yeah, well, we knew that in the 1920s and the 1930s with the beginning of quantum mechanics. And you don't even need quantum mechanics. You just need to understand surface energy and the formation of surfaces, which we were starting to understand in the 1920s. And you can predict that the inherent strength of a carbon-carbon bond is about 3 million psi. Great, as long as it doesn't have a defect in it. A little microscopic defect like a missing atom, in which case that 3 million psi becomes 100,000 psi, okay? And it rips. Well, the physicists have done that because they haven't tested any of these things, okay? They just calculate it. So they put it all in the Wall Street Journal. They get Congress and everybody else to give them all kinds of money, and it's money down a rat hole, okay? So I'm not real big on nanotechnology. And there are some uses for it, but not in structural materials. So it turns out I was on this committee, and I wrote up my little submission, and my submission was sort of what I was teaching to my students about material selection, and this was supposed to be on structural materials, okay? Or I was on the subcommittee on structural materials. And so what they did, this is entirely written by me, they don't bother to, it's Appendix C, Integration of Material Systems and Structures Development, okay? So it's structural materials. If you want to read a whole module of my introduction to structural materials, material selection and design, here it is. This is the 4-page synopsis. So you don't have to read anything else, you can just read this. But it talks about cost, relative cost, which is an important thing when you're building big things, okay? So anybody know what the cost of the value of a pound saved in an automobile is? I was driving in this morning, they were talking about we're having problems, the highway trust fund's going to run out of money because we've increased the fuel efficiency. And so they're not paying as much gasoline tax, and so we can't rebuild the roads. We're going to run out of, middle of the summer, the trust fund's going to run out of money, so they're going to take it from the post office. Oh, well, this is clever. Okay, the post office had a $5 billion deficit last year, so they, maybe they're going to take it from the pension fund of the post office. I don't know. These accountants are great, aren't they? Anyway, what is the value of a pound saved in the weight of an automobile over the life of an automobile, which is about 100,000 miles? You'll find it's about $2. Okay, for every pound you can get out of that car, you can save $2 worth of gas. Okay, what is the value of a pound saved on a Boeing aircraft over 100,000 hour life of a typical commercial jetliner? $200. So on jetliners, they actually have people, vice presidents at U.S. Airways, who decide how many magazines you can carry on the airline. Okay, because magazines add weight, and at $200 a pound, that's a significant amount of money. Okay, and a spacecraft, you'll find in this article, is $20,000 a pound. Put a pound of payload or orbit up there is about $20,000 a pound. Okay, so when we talk about selecting materials, oh, by the way, ships, to transport a pound of goods by ship across the ocean costs how much? 20 cents. Right, about 20. Is that what you said?
No, that was a guess, just based on the ratios.
The ratios, right. So you go from 20 cents a pound from kind of railroads and ships to $2 in transportation of cars to $200 in commercial aircraft. Military aircraft might be $1,000 a pound. And then it starts depending on where you're taking the weight out. Are you taking it out of the brake pads, or not the brake pads, but the calipers for the disc brakes? That's worth more because that's non-sprung weight, okay? And it vibrates, it moves faster. This is, you're not going to get this lecture, but if you wanted to take this course again and take different modules, I'm giving you kind of a capstone, a thumbnail version of some of those things. And that's what this material selection is. But the real point is, if I'm going to make something and sell it for less than $2 a pound, my metal choice comes down to steel. Because another rule of thumb in there is the metal cost for the fabricated structure is about 10% of the overall structural cost. Okay? So one time, NAVSEA, back in the days when the aircraft carriers were starting to gain weight, the Nimitz class carriers gain weight at 250 tons a year. So whatever I gain each year doesn't sound like a whole lot. But a Nimitz carrier, if you plot the weight of a carrier over the 60 years of the, or 70 years or whatever, of the Nimitz hull, they gain 250 pounds a year, 250 tons a year. And it's not down in the keel, it's all mostly up top, guys, okay? So that's not good. That means you have to put more lead in the bottom, okay, or whatever. You're trying to save all this weight in the ship and then you put more lead in the bottom. Anyway, so they decided they wanted to go to HSLA 60 for a lot of the lower strength steel components. And Newport News estimated they could save 2,000, the designers decided they could save 2,000 tons on the weight of the next Nimitz class carrier if they had an HSLA 60 available. And so David Taylor with the steel companies developed an HSLA 60, which wasn't too hard to do. It was sort of, there were commercial versions. It was good dual use technology. So they basically said, well, we need to do a study to find out what this, if we go to this change, what's it actually going to cost as fabricated. And my rule of thumb is that if the material costs you $1 a pound, it would cost you $10 a pound as fabricated. Because let's face it, you start out with these rectangular plates and you cut away 30% of them and send them back to the steel mill for scrap, right? So that just increased your price by 50%. Of the per pound of what you buy. The Air Force calls it buy to fly ratio, okay? How many pounds do you buy versus how much actually goes and flies in the airplane. So I guess yours is buy to float or something, okay? Well, they came after spending $1 million of, NAVSEA spent $1 million of Newport News money. They found that if the HSLA 60 was going to cost them $1 a pound, $2,000 a ton from the steel mill, it would cost them $10 a pound as fabricated. All they had to do was read my little thing. It's right there in that paper, okay? Now some things like the pipeline industry, the material cost is 30%. But just as if I needed a rule of thumb, and I got the breakdown in there. You know, you spend as much on non-destructive testing as you do on welding. Okay, you spend as much on design as you do on welding. Okay, you spend as much on forming and shaping and stuff as you do on welding, right? Machining. Anyway, the breakdown is in there. Okay, and you got to pay the manager something, right? So the point is, if I want to sell a car for $2 a pound, or if I want to save weight on a car and it's only worth $2 a pound over the long run, I can't use a material that costs more than about 20 cents a pound, and that's steel. You can't afford aluminum. Back when I was developing all this stuff 10 years ago, when we had gasoline at $2 a pound. Now maybe you can afford steel now at $4 a pound gasoline, but guess what? The price of steel has gone up. Okay, so it's now about 40 cents a pound for the sheet steel they use in automobiles. So the numbers all still sort of work out. It does make sense if you're buying gasoline in Norway, which is probably at $8 a gallon, not because they don't have a lot of gas, because the Norwegians want to conserve, and it's sort of a national policy to conserve. If the world was, the only reason the world makes steel cars is because they want to sell into the North American market, and that's us. Okay, aluminum cars make lots of sense everywhere else because the price of gasoline is higher. Okay, but everybody wants to make something that's going to be competitive with the Ford Taurus. Even Ford looked at a all aluminum Ford Taurus years ago, and you know, instead of a $25,000 car, it becomes a $35,000 car. Okay.
They built aluminum F-150
truck, not yeah. Well, they're coming out with it now.
Oh, I'm sorry.
Okay.
Yeah, I don't know.
They're coming out with an all, but we haven't seen the price yet. And I'll bet you it's a $40,000 truck, even though the steel one you can get for $30,000. And when I was saying all this, it was 25 years ago when I say we wouldn't see all aluminum vehicles for another, I was saying in another 20 years, okay? And I wasn't talking about all aluminum Audis. At the time I said, anybody can build, I told you yesterday or the day before, anybody can build a $100,000 vehicle out of aluminum, okay? How do you build a $25,000 vehicle out of aluminum? Well, so when the Navy about, 15 years ago decided they were going to the littoral battlefield, and they had to have, 50-knot ships, okay, and they had to be aluminum. Well, they didn't have a lot of experience with aluminum in the Navy, and the experience they had with aluminum in the Navy wasn't very good. It was superstructures catching fire, okay, and becoming a big flare, okay. I told you about the Belknap disaster. Anybody else know about the Belknap disaster? Okay, it's in the book on disasters. But if you're finished with that, I'll take it back sometime. Okay, if someone's using it, that's fine. Okay, I do want it back. Otherwise, I have to buy another one. I actually told them, the money I give you, if you want one for the library over there, okay, you can buy yourself. There's one, the Air Force disasters. Anyway, there's a series of these books. But the Belknap was a destroyer that had an all-aluminum superstructure. That was what they were building in the 70s and the 80s, early 80s. And on some maneuvers, it collided with the original JFK, okay? The original Kennedy, not the new Kennedy, okay? Which the original JFK was launched about 72 or, no, about 70. I went to Virginia Beach High School, and one of my classmates' father was the captain. Okay, and he was, while the ship was being built, he was stationed in, well, he lived in Newport, in Virginia Beach, but anyway, but he was the assigned while the ship was being completed. They had a collision a few years later, right underneath one of the elevators, the hangar deck elevator or whatever, and some jet fuel fell on top of the Belknap, and the aluminum superstructure caught fire, wiped out the whole ship. And the joke at the time was a gallon of jet fuel could wipe out any ship in the fleet. And of course they knew about that because of the Sheffield, and I've had several people in this class do presentations on the Falkland Islands War and how the British cruiser Sheffield got hit by an Exocet missile. And people say that the aluminum superstructure caught fire Although there are other things now you can find on the web say that wasn't the cause of the fire on the Sheffield. It wasn't the Exocet missile. Whether it was or not, it's still a debate. And I've asked some of my friends at Carter Rock, and they sort of, well, you know, they'll tell me there's some debates about it, but let me tell you, the Navy believed it was the aluminum catching fire because by the mid-'80s, they were trying to replace the superstructures in surface ships from aluminum to waffle membrane steel, high strength low alloy steel. Okay, so they were making sort of a waffle composite of steel to get rid of the aluminum. Well, why would they be spending all that money if they didn't think the aluminum would catch fire? I forgot, I should have, I got to get from Harold Larson, but he won't be in until, well, he'll be in tomorrow. I have a piece, one of the students here had recovered from one of these ships where you have the holes, you know, through the, it was in one of the, what do you call the toilets on the ship? The head, okay, the head. He was in the head and he noticed a breeze coming through the wall, okay? And it was, the other side was basically some steam from the engine room or whatever. And the breeze was coming through because it had completely corroded away. But it was at a steel aluminum transition joint where there's tremendous corrosion. And he just picked this up out of the scrapyard and took it home, and he had a piece like this. So I got a piece, Harold Larson probably still has it anyway, but I have a little piece that we polished, and you can see the corrosion. It just corroded through the steel like mad. Anyway, so where was I? I was talking about the cost of steel. You end up finding that you can't afford these other things. Now, submarines, you can afford a little more than you can for surface ships. That's why they still use HY80 so far as that goes. But there are welding problems with all these things. And we'll talk about some of those welding problems in a little bit. But before we take our break, let me start my demonstration, because we're going to talk about hydrogen eventually. And I showed some of you the video before we got started. But I have to do a demonstration that you'll really remember. So this is only the second time I've ever done this in class. There's nothing dangerous about it. Diet Sprite, okay? 2 cans of Diet Sprite. And if I pop the top, there's CO2 in the Diet Sprite. And essentially, what you're seeing is gas coming out of a liquid, whereas when you weld steel with hydrogen in the atmosphere, you will put hydrogen into the steel, and the hydrogen will come out. And I showed you the video from the 1950s from University of Delft. And you can see how rapidly the CO2 is coming out, right? You've poured sodas before, right? So here it is. It dies down very quickly. You still see bubbles in here, right? I can shake it up a little bit and generate some more bubbles, but they die down pretty quickly. So before the end of the next hour, you will no longer see bubbles. But when I shake it up at the end of the next hour, I can still generate bubbles. There's still CO2 in there, okay? But it comes out very rapidly in the first few seconds. By tomorrow, this will be completely flat. No more CO2. It will slowly evaporate away, okay? That is almost a perfect analogy for how fast hydrogen comes out of steel, okay? This is out of a liquid. Out of steel, it's coming out of a solid. But if you were here and saw the video, I can play it at the break for some people if you want. It said you had to put that thing under the microscope slide within the first 10 minutes or an hour, or you wouldn't see the bubbles coming out. It turns out that if you're welding a high-strength steel to build a bridge, the American Welding Society says you must wait 48 hours if you use 100 KSI steel before you do your non-destructive testing. Because otherwise, if you do your non-destructive testing in the first hour or two, the cracks may not have formed yet. They might form 10 hours later. For nuclear submarines, you have to wait a week from the time you complete the weld to the time you do your non-destructive testing. Because higher restraint on the submarine, you might get hydrogen cracks days later. Usually the hydrogen cracks are only a problem in the first week or a couple of days. I can tell you a story, I probably will tell you a story one of these days, of where it lasted for 9 months. Okay, but it was frozen in the high Sierra Mountains in the winter. But anyway, so you can trap it if you freeze it. We'll talk about that too.
Is it just for arc welding or stick welding, or is that solid with the tungsten?
It shows up with all processes. The Seawolf submarine, the problem was with MIG welding, okay, gas metal arc welding, where you had no flux. But I'll show you a plot. Actually, I don't know if I hand it out, but anyway, I'll show you a plot of how much hydrogen you get with different welding processes and stuff. So we're going to spend a fair amount of time on steel. We will get to aluminum, but that'll be probably next week. Okay, so let's take a break until about 8:39 or something like that.
I started thinking, I was like, probably not going to be too wet.
So where's my silly putty? I don't want it to all dry out, you know.